the first lecture was very conceptual, right? We're just introducing NLP as a research topic, and basically was describing mostly how language can be modeled, right? And how it can be modeled efficiently by a computer. So we discussed this modeling using a probability distribution, right? Where you have an n-gram model, right? What is the probability of a sequence of words as estimated from a large body of text. Then we discussed the problem that the language is discrete, there are grammatical rules, and it's a very complex source of information. There are many different aspects and level of words. I just want to go through quickly. This is something that we did last time. I just want to get to the, let's say, the first modern application of this, right? So the first idea that people had is that we can try to define a semantic representation of the word using relationship and concepts. So people come up with WordNet and ConceptNet, which is a large lexical database of English nouns, adjective, adverb, and there are grouped by synonyms, okay? So, and then you have a relationship between these words. For example, you see here, right? So it's like a knowledge graph. So you have different, the nodes in the graph are terms and are words, and the relationship are belong to a certain set of relationship, right? So for example, you have that part-whole relation. So chair, backrest, right? So the backrest is a part of the chair. Then you have synonyms, which are words that have roughly the same meaning. For example, expert, practitioner, proficient, they're all similar. And then they have relationship like fine-grained relationships. So anyway, so there are a large set of words, a large set of relationship. And of course, these are very extensive knowledge graphs, and they have to be manually generated. They have to be human curated. And people keep working on this, and they can be used for semantic language understanding. But of course, the issue is that they have to be manually generated, right? So you need to have a certain set of humans that agree on a certain relationship between terms, and so and this has to be written in the data set. It has to be decided, and of course, there are also aspects of different languages, right? So there are the same concepts that are the same across different languages, and then somebody that some languages don't have an exact correspondence between terms, so you understand that trying to have this explicit graph capturing the complexity of languages, it's a daunting task, right? Because you need to have external resources to build this, and this requires an infinite amount of work, and then it doesn't take into account the temporal aspect, right? So if the meaning of a word changes, then we will need an expert that goes into the graph and checks that the meaning of a certain word in 2025 is the same as in 1985. And then also, for example, there are new words that emerge, words that disappear from usage. So it is very laborious, okay? But of course, if we had this type of representation of language, right, then what we could do is that we could represent a text using a one-hot embedding, right? So we will have a size of the embedding, which is the size of the bag of words that we're trying to use, and then we can just one-hot encode everything, right? So in this case, let's say that we have a vocabulary of, let's say, 15 symbols, right? And then for each element in the sentence that we want to represent in the computer, we just do one-hot encode, okay? So this is, of course, a disaster, right? Because it doesn't scale with the size of the language, right? The English language is like 6 million words. Chinese, if you consider ancient language, probably like 1 million characters, right? So it's not doable. But of course, this has the nice advantage that these one-hot encodings, let's call them embeddings, right? These embeddings are orthogonal, meaning that when we take the product, the inner product between these two representations, we will get a 0, right? Because it's as if you have an orthogonal dimension for each of the words. So this is of course, this gives us a first idea on how we can move beyond this simple idea of one-hot encoding. And there is this idea that we can try to build a space, and in this space we represent our words using vectors. Okay, so we can try to encode the semantic and syntactic similarity of, let's say, text using a vector space. And basically, we want to do this without human annotation. So we want to fully automate the building of these embeddings. And can we really do without men? As we said, the language is very complex. It requires a lot of resources. So how well can we perform if we take the human intelligence out of the loop? But of course, all this, our understanding of language is fully embedded in the vast amount of text that we have generated in the last few thousand years. And since the advent of the digital age, all this text has been encoded into digital format, right? So it is available to the computer in digital format. And so we can do without human labeling of this data, of these relationships, and we can try to go for a self-supervised task, right? So we will assume that we have a very small percentage of labeled data, which is being annotated by humans, and all the rest is supervised. Very good. So now we have a few different paradigms. So before, when we were estimating the semantic model, we use a count-based approach. So we will have, remember, we have the n-grams. We see what is the frequency of this n-gram, and then we build this probabilistic model. But of course, we can just have a simpler approach to the prediction of the next token, and we can just use a neural network. And we can just teach a deep neural network, let's say a sequential network like GRU, to predict the next token given the large body of text, so that we move from this count-based approach to some sort of predictive model that minimizes a certain loss. And then, of course, let's say that the way in which we extract information from the data to build a predictive model will not be done using statistics and probability theory, but it will be done using learning theory. Despite the difference between these two approaches, we realize that the common core is the co-occurrence, right? So basically, you want to know that if a word occurs in the text, what is the probability that other words are in the context of the word? And the idea is that the word meaning is captured by the context of the word, right? By the words that frequently appear with a certain word. And of course, this tries to abstract away very complex grammatical rules, the declination of verbs, the gender, everything tries to is abstracted out into this type of relationship. Okay, so this is the most important artifact of NLP, right? And we understand that this idea of representing words in a space where distances relate to a semantical relationship, it's the best, the best tool currently available to go about this. Okay. So you see, for example, here an example of a few sentences, right? So you see that the word that we are looking is bank, and we are looking at a context windows of 3 words before and 3 words after the word bank. And then we can go around the body of data, and you can see which words co-occur with bank, right? So we can predict with the other words in the context of the word bank, 3 words before and 3 words after. Of course, there is money. There is the word withdraw. There is the teller, right? And then there is the robber, right? So a criminal activity. And then you see that in the last sentence, we have later today, let's go down to the riverbank to fish, right? So it's understandable that the meaning of the word bank is determined by the context. And the context of the last sentence has nothing to do with money withdrawing, bank tellers, ATMs, cash, right? There's something to do with water, with fishes, with boats. And that's because in the last sentence, the meaning of the word bank is that of the river bank, right? Is that of a barrier. So we realize from the context the difference of this. Okay, so let's keep this, right? So we don't need to do this. But basically, if we focus on let's say over n-grams, what we can do is that we can apply classical machine learning techniques to try to automatically build a graph of relationship, right? So, for example, here we can do SVD over the matrix that predicts the distribution of a context of a certain token, and you can see that if you do SVD, you do realize that the inherent structure of the language, right? So, for example, here the decision tree puts the countries all together. These are nations. Yeah, go ahead. There is a question.
Hi, does SVD means singular value decomposition?
Yeah, of course. Like PCA, the same thing as PCA.
Oh, okay. Thank you.
Make sense?
Not yet.
No, but you understand PCA, right? You understand PCA?
I have heard about it.
You should have taken the machine. I mean, you should have taken the deep learning class, the machine learning class before doing the deep learning class. Right? But the idea is that, yeah, it's a low-dimensional projection, right? So you have the matrix of probability distributions, right? And then you project this very large matrix down to a lower dimensional space. And then what you do here is that you represent the distance using a decision tree, right? Something like that. So you represent the distance of the term on the lower dimensional space. Anyway, you just go, yeah. So another way of, if you don't want to represent it as a tree, you can represent it as a two-dimensional projection, right? So you have this very large matrix, and you project it on the first two dominant PCA components, and then you can see that the similarity of words that have the same grammatical root, and so on. Very good. And then, yeah, for example, if you zoom in some of the areas, then you see that all these words that have to do with swimming and cleaning, and basically you see some semantic grouping, right? And let's see, is there anything interesting here? Is there a relationship? So learning and teaching is very close. Priest and bride. Very close. No sign of a husband, of course. Student teacher, student doctor. So there is some sort of semantical structure in this low-dimensional projection. So the idea is that in order to obtain this compact description, it is very extensive because we have to remember that we have to go through all the possible n-grams and see the co-occurrence, right? So it's very extensive. We have to go through the text multiple times, one for each possible word. Sorry, so the scaling is, let's say, an n cubed to the worst, and then you can do some trick to bring it down a little bit. So this is too unwieldy. So what we can do instead is to just use a neural network to represent the embeddings, okay? So we just want to go through the text once and train a neural network, and use the neural network to predict the context, and this will produce a more efficient way of representing this high-dimensional distribution. Okay, good. Yeah, let's not. So the breakthrough here is Word2Vec, right? Which was released in 2013. So this is the idea that this is a neural network that taking a word in the English language, projects it into a space of 300 and something dimension. And yeah, so this is let's say the most important way of representing language in a computer that has emerged so far. Yeah. Yeah, so this is Word2Vec. This is the paper from Banjo, right, where they describe how the network is being trained. And the idea is that you want to have an embedding layer. There is the word comes in, right? Then there is a window of context over the text. Then there is an embedding layer. So this embedding layer generates a vector in the vector space for each window in the context. And then And then you see that, yeah, what comes out is the embedding of the words, is the embedding of the word that we have selected from the context. We're going to do this more layer. And of course, we need to have more parameters in the network to be able to train a network that does a good prediction of this. And so we have some intermediate layer. Then we do some softmax. And what comes out of the softmax, as always, is the probability distribution of the next token, for example. Okay, so we want to train a network for next token prediction. And we do this through this intermediate representation of the context of the word using a vector. Okay, so this is word2vec. And it's really the first time that NLP, right, natural language processing, started, right? Because before there were the steps, the progress in NLP were very limited. But since people introduce word embeddings, the type of networks that we intend to train has increased tremendously. So yeah, so then there's some more slide of context. You can go through this, right? So the skipgram, continuous word of bag of words. You can go through these slides just for your personal knowledge. But basically, what comes out of word2vec is again this high-dimensional vector for each word, and then you can again do, for example, PCA over 2 dimension and see the following, right? That the distance vector between China and Beijing is the same as the distance, is very close to the distance vector between Russia and Moscow, between Poland and Warsaw. So the idea is that if you have a country and the country has a certain embedding, you add a certain vector. This vector will bring you in the neighborhood of the capital, right? So the way in which you move over this embedding space is consistent with the semantic mean, right? There's usually this one here, right? So there is this very cute example there in word2vec. You take the embedding of the following 3 words: king, man, and woman. Then you take the embedding of king, you subtract the embedding of man, you add the embedding of woman, and you obtain something which is similar to the embedding of queen. Okay? So the idea is that once the network has been trained, then it implicitly embeds in the geometry of the high-dimensional space the semantic and syntactic relationship of the language. Let's not do this too much. You guys go through this, but basically, once the idea started, then people kept refining this distance. And the idea is that single word embedding is the most important thing in NLP. And we will often discuss about this token-based model, right? So when you're given a certain set of text, you'll have a tokenizer. So you guys already saw the tokenizer for the Shakespeare case. And you use not on the type of the words because it is too limited to work on a given type of the word. Instead, you work with tokens. Okay, good. Then we're going to do LSTMs, long short-term memory models, and then you're going to do contextual word embeddings, and then the breakthrough that we have is, of course, this general purpose transformers, right? So the transformers, we're going to do it in 2 challenges. The next challenge is word embedding. In 2 challenges, we have transformers. Okay, good. Let's switch presentation. We go to 24 and we do attention. So if you can do attention by today, we will all be very happy. Let me just check class a second. Anybody joined? Anybody left? No, good. Yeah, so if anybody has any question, let me know. Otherwise, we go to the next. So attention is kind of tricky, so we'll try to do it very precisely so that you guys can understand attention, which is relevant for the challenge this week. Okay? Yeah, so if some people join now, just let us know if you want some help in pairing with the groups, right? So in this document, right, that we have pinned, here I'll paste it again. We have the current formation of the groups. So if you don't have a group, contact one of the leader of the group between 1 and 4 and let them know that you're looking for a leader. You're looking for a group, and they should sort you out. Okay, so let's work on attention, which is a very important concept. So we discuss about word embeddings, right? So the idea is that there is a certain set of text. The text has a certain context, and then you project this. And we discussed the word embedding can be based on the counts, where you do, let's say, some SVD, PCA, or you can use some predictive model, which are, for example, word2vec. Okay. And so the idea is that you have a vector representation of all these possible words, and then, you know, for example, for apple, for before, for zoo, you have a representation as a vector. Very good. So let's say that then we want to work with this data set, which is the Yelp data set. Now it's an app that people don't use. People now use just Google reviews on Google. But basically, it was an app where you could review restaurants in your neighborhood, and you will leave a set of scores for your experience at a certain restaurant. So how would we try to, let's say, use word embedding in order to predict the score? So as we said, right? So we want to have a model that avoids the complexity of the language itself, right? We don't have a model that said that there is an article, food is a noun, was is the verb to be in the past tense, the lesion is an adjective. We want to avoid this, right? So in order to avoid this, we train the network that sort of produced a vector representation for each of the words. So when we see this review, we put it in our tokenizer. Our tokenizer breaks down the sentence in words. Then for each word, we pass it to the, let's say, word2vec. We get a representation over the space of 300, of a vector of type 300 for each of the words. And then what do? Since we want to predict the score corresponding to this review, we sum the embeddings all together. Okay, we obtain an average embedding. Sounds kind of strange at the moment. And then we want to train a feed-forward network in order to predict the score, right? So then now we see how useful the embeddings are, right? Because this idea that we can operate geometrically, let's say using words, has allowed us to use, let's say, the machinery that we discussed so far in order to train a network for a certain downstream task. Okay, so then if you take another review, which is a waste of money, tasteless, you can do the same. You can take the embedding for each word, sum the embeddings, take the average, and then you can have another point in your data set. And things proceed in this way, okay? Of course, if somebody uses words that they don't appear often, or the context is unclear, then the embedding has no understanding of this type of nonsense language. So those are the limitations. So the idea is that we'll leverage the existing data in order to train the embedding, and then we don't need human intervention to create the embeddings, right? So if somebody gives us a text, we don't need a human annotation. You can just train the embedding to provide this representation. And the issue that we have is the out-of-vocabulary words, because new words continuously emerge, and the words that are emerging in the language, they don't appear often, so we don't know what is the context, we don't know how to predict their occurrence. And of course, the fine-tuning is very hard, right? So let's say that you spend a few $1 million to train an embedding using all the documents available in the internet, but then when you move to a certain data set, right, the type of language used in a certain data set, for example, used for these reviews that has to do with food, with atmosphere, with restaurant, with service, with alcohol, with drinks, will have a use of the language which is, let's say, much more narrow, the general use of the language, and you will want to specialize your embedding for this context. And doing this is, of course, very expensive, okay? Because you have to retrain the network. Good. Sorry, I did something. Let me share again. Okay, good. So these are the issues that we have. So the word embeddings are used in this way, right? So you use a recurrent network, you use an LSTM, and you go through this, and you train your neural network, and then basically since you use let's say a sequential network, then every token is contextualized by the embedding. Good. So this is Yeah, so this is the idea is that yeah, you have this sequential network. Guys, I think I skipped. We go back to this. So this is the use of the embedding, right? Just let me check that I didn't skip a set, because I thought there was this the slide set on the embeddings. Did I skip something? So this is attention. Give me a second, guys. Sequence to sequence. Lecture 24, right? So we just did 23. So was there a mislabeling of the? Was there a mislabeling of the slides? Let me check briefly. Possible that something was mislabeled. Just a second. So this is lecture 23, right? And then now we are lecture 24. Guys, I'm a little bit baffled. Just a second, let me double check. It's NLP 1, 2, 3, 4. Okay, STMs. Okay. Got it. There was some mislabeling somewhere, because I thought we will do LSTMs. We will do LSTMs. This is the, sorry guys. Yeah, there is something in the slides. Representational languages is what we just did, 24. Guys, if you can find the slides on LSTMs, it would be great, because I thought that this was the set of slides on LSTMs, but it is not. Let me check. What happened to LSTMs? Sequence to sequence. Okay, I found a set of slides. Sorry, guys. Let me post it, because I think they misplaced the links somewhere. But no problem. I'll just post it here I'll just post it in Slack so that we don't lose it. Yeah. LSTMs. Channel organization. Channel LSTM. Passes. Node 835. Okay, good. Back in business. View full screen. Shared. Okay, guys. So this is they have to go to the year before, and then you find this set of slides. Okay, good. So we are saying that we want to use the DNN to model is this factorization of the joint distribution into product of conditional distribution. So basically, this is going to be the next token that we are trying to predict, and this is going to be the context, right? So let's say these are going to be the 3 words before the current word, and basically we want to train a network that we run it through the text, and it learns how to predict the next token given the past token. Okay. So this was originally developed for time series prediction, right? So you will want to know, for example, what is the probability of this sequence of of weather, right? A day you have a good weather, then followed by bad weather, followed by cloudy weather, followed by good weather. So what you can do is that you can take the weather across all possible days, and you can try to predict the weather of the next day given the previous day. So, so the idea is that we will gain accuracy, right? If we extend the window of prediction, right? So in day one, we just observe the weather of first day. The second day, what we can do is that we can look at day two and look at the weather in day one and predict day two. And at day three, we have a longer history, so we could try to pull from a longer history and predict the weather from a longer history. And so the idea is that ideally, right, we would like to predict the weather tomorrow, given all the past days in the history of the Earth. But of course, we have some complexity limitation, and we want to reduce the complexity of the network, and so we have to limit our context to a certain number. Okay. So in general, the structure that we're going to look applies to any sort of temporal data, but in the next we just focus on natural language. So, so as we said, this is the language model, right? So they already went through this, right? So the idea is that we take a sentence, we tokenize it, and then we look at the probability of the next token given the sentence. This is the bigram class that we did last time, right? And now we want to do this. Okay, so the idea is that you will want to take an input word, you want to pass it to a hidden layer, and then you want the output to go to a sigmoid, and the sigmoid should be the probability of the next word given the previous word. Okay. And as we said, we want to do this with an RNN. So we want that we have this structure, this sort of sequential structure, this recurrent structure, where we have all our tokens here on the bottom, right? All these tokens, they go into the network at a certain time. So this is time 1, times 2, times 3, times 4. There is a hidden state. And then from the hidden state, we have another nonlinearity, and this produces an output. In order to maintain, let's say, the influence on the context, what we can do is that we can have a hidden state, and we can have that we can have these hidden states as two input. One input is from the previous time instant, and one input is from the current input. Okay, so you see that here the output at time t is obtained as a nonlinearity from the hidden state, which is updated from the previous hidden state and the current input. Okay? And so the idea is that people call this recurrent because it's as if you have a sequential data coming in, and this is recurrent in the sense, for example, keep coming back, right? In the meaning of keep coming back, because this state, the hidden state keeps looping up, right? So it's a loop of the hidden state onto itself. So if you unfold the network, then you have all these different time sequences. But if you do an inference, right, what you do is that you keep recurrently updating your hidden state. Okay, so there is a loop in inference. Okay, so we understand the inference process, right? In the inference process, you take the token, it goes in, you apply the hidden state, you obtain a new hidden state, and then you apply nonlinearity to get a prediction of the next token. Very good. But how can we train this? Okay, so the idea is that in order to do the training, what you will do is that you will unfold the network up to a certain, let's say, depth, and then you will obtain a computational graph from the unfolded network, and you will try to run back propagation over this. Okay. Of course, there is the issue that the network is predicting the next token, so there is a possible inconsistencies between the token predicted at time t and the input at time t plus 1. So for, of course, in order to run back propagation correctly, we assume that the predictions are not consistent, right? So it's as if at each point in time you receive the correct input and you try to predict the next token. But then when you apply back propagation to the next time instant, then you assume that you have done the correct prediction. Okay, so you don't break this loop. And then you have to calculate the total loss, and the total loss, you just take, let's say, the BCE average over all the possible predictions, right? So here you have that you have predicted token 1, and instead the true token was Y1. Here you predicted Y2, instead it was Y2, and then you do your usual, your usual BCE loss here, right? So you want your network to actually predict the next token. And once we set up this, right, then we can run our backpropagation, our computational graph. That will tell us how to run our backpropagation, and then we will update things. Okay, so the chain rule will tell us how to update the network parameters so that the prediction, that the network improves its prediction performance. Of course, you have to decide, let's say, what are the computational resources available to you, because when you unfold the network, you cannot unfold the network for, let's say, thousands and thousands of characters. So you have to decide a certain depth of this unfolding, and of course, many training details on vanishing gradients and so on and so forth, but this is the general process. And how do we visualize the process, right? So for the derivative of the loss with respect to the parameters, right, starts from the last token, and then it backpropagate from let's say a token in the past back to the update of the hidden state in the previous tokens, and then you repeat this operation token by token, and you try to apply backpropagation, and everything goes nice and smooth. So this is usually called backpropagation through time, right? Because you are sort of traveling back in time in the unfolded network in order to correct the parameters so that the influence of the context on the prediction is consistent, right? It's a positive influence. And of course, it's very expensive, right? Because the complexity of the network is multiplied by the time lag that you have in your prediction. And so the updates are usually done sentence by sentence, paragraph by paragraph, and this is generally not equivalent to operating over a certain size of time t, because this hidden state works as an infinite memory, which is continuously updated, right? So you could run the network a little bit, then you get a certain value for the hidden state, then you try to do this BPTT process, and you update the network based on the context of the sentence that you were working on. And you already have seen this. So there are some special symbols, and the special symbols that we are considering here is the EOS, end of sentence, because of course you also want the network to generate an end of sentence. So when the network generates an end of sentence, then it means that the sentence is being generated. Which means that we can, once we have trained this network, we can also start from a random context and let the network evolve to generate tokens. We can feed the generated tokens back into itself, and we can let the network generate a sentence. And when we reach the EOS token, then we know that the sentence has been generated. And so we start with the start token. We initialize the hidden layer to something random, and then we keep going by generating a sentence, okay? Sorry, Harry shouted, right? So this is the sentence generated through this, right? So during inference, you put the start token, random network, and random hidden state initialization, and you read the network. Good. And there was a very famous example, right, of the improvement of this network when people started generating this fan fiction from Harry Potter, right? Because we're talking about 2005, right? So Harry Potter was very popular. So people trained an RNN to generate text that was similar to Harry Potter novel, and now you can go back and read it, and you can see like the improvement of the quality of the prediction as networks were getting better, as people were learning how to train this RNN more effectively. And yeah, so also you can have generated recipes, right? So you can have a network that generates recipes. There is a GitHub link here. Yeah, so on and so forth. So let's see what are the strengths and the weaknesses. So the idea is that you can, since this is a sequential model, you can handle any infinite number of sequences. The memory is controlled by the size of the hidden layer. And yeah, so it tends to be pretty stable. The idea is that the training is complex, so that's a downside. And the managing the gradient explosion, the gradient vanish is very tricky. And then learning, having to understand the long-term context is tricky. So training RNN is generally pretty tricky. Okay, very good, guys. Let's do a little break before we go to the next topic. So this is just an example of the vanishing gradients, right? So the next time we do LSTM. So let's take a 5 minutes break. I'll see you back at 9:30, 30, and then we take it from there. Okay, guys, we do another set. Okay, ciao, guys. Little break. Yeah, so guys, I'm still looking for the leader of group 2. We don't know. I'm looking for the leader of group 2, guys. Anybody knows the student? Wang Shenshen? Yeah, because you guys don't consistently use your proper name for this. Yeah, anybody else is looking for a group, let me know. Huh? No. So because in the documents there are, let's check. Documents we have, so group 1 is okay, right? We have 4 people, so group 1 is good. Group 3 is 5 people, so it's a lot of people. Group 4, okay, you guys gain one student, right? So my advertisement, your advertisement worked. So the total is, so 4 plus 5 plus 3, it's equal to 12. So yeah, so there should be few students still looking for a group. Okay. Okay, any questions? Otherwise we go on. Yeah, so the next 2 challenges are already posted, so you can work on the 2 challenges at the same time, right? So one is on word embedding and one is on BERT. Yeah. Okay, so let's go back to LSTMs. So LSTMs stands for long short-term memory. So let me go in full screen. Okay, good. No, I have to share the new window. Okay, so the idea, remember the downsides of the GRUs, right? So the downside of the GRUs were that they couldn't really capture long-term context because in a sense the memory, right, the hidden state was not, was just controlled by a nonlinear network, right? So the way in which you update the hidden state, in a sense, didn't allow you to capture long-term dependencies. But this is where the LSTM kicks in. So the idea is as follows, right? So you can see it here. So you see that you have a current input, you have a state, which is the age, and then this is telling you how the state is updated, right? And how the context is updated. Yeah, so the idea is that these are sigmoid operations, right? So the idea is that the network has the ability to learn to forget some memories and to retain some memories, so that if there is some crucial aspect of information that you want to pass down to the future, to the next tokens, then you can do so with using a gated recurrent unit, right? So a GRU. And so this is the idea, right? That there are some old memories and there are some new memories that you're making, and of course, what you decide to pass down, it's a weighted term of the long and short term memories. Okay. And these are the gates that influence your just a second. My father was, because I'm leaving today. I'm heading back to Taiwan, so I'm gonna be back in Taiwan next weekend. So I'm actually flying in a few hours. So people are checking on me. Good. So LSTMs, they still suffer the problem of vanishing exploding gradients, but it's less likely than RNNs since there is this type of forget mechanism. And LSTMs are better at remembering long-term dependencies. Yeah. So they almost always perform vanilla RNN, capture long-term dependencies. Of course, the idea is that learning this forget mechanism is very tricky, right? So the stability of training LSTM, it's very, very tricky. Okay, so this is LSTMs. So this is, we were discussing about the score for reviews, right? So you can give different scores to different networks in this task of predicting the next token, this next token prediction task. So the idea, if you use n-grams, right, the score is very low. Then you can have some full neural net, some single token neural network, right? So you can have that. The structure here, which doesn't do well. So we have RNN that do better, right? Because you finally have a sequential structure, so you don't have to worry about the size of the input, and then LSTMs do very well. Okay, good. So the idea is that the next token prediction, right? It is one type of task. Okay, so we said that the next token prediction task is most useful for, let's say, language generation. But in general, you're not interested in doing only next token prediction. For you, what you know to do is, for example, classification and prediction. This is what we discussed before. So you want the network to have some other downstream task, right? So maybe you want to add at the end of the network that you have to do some prediction. Okay. So this is what we discussed next. So the idea is that you train the linear model to learn the hidden layer embeddings, right? So you do so through this next token prediction. And then what you can do is that you can use the hidden layer embeddings for other tasks. Okay, so this is the step that we do from next token prediction to embeddings. Okay, you see here very well, right? So so what is the structure, right? So in this task here, this is the simply next token prediction, and this is sort of a unlabeled task, right? This is a self-supervised task. You don't need to have labels, right? So this is an unsupervised task. But here, right, what you do is that you learn from the hidden layers of the network, and then what you can do is that you can stack them all together. You see this blue here, right? This blue here are the values of the hidden state for each of the intermediate steps, and then you use this as an input to another layer, and this layer could do some other task, which is, for instance, next token prediction. Sentiment classification. Okay, good. And so the idea is that you have the whole sequence goes in, you let the network evolve, you steal all the hidden layer values, you feed them to a single downstream unique dense layer maybe, and then you do your sentiment prediction. Very cool. Good. So now this is how we obtain embeddings, right? This is how we obtain embeddings, and there is a lot that you can use these embeddings for. And as we said, you can train these embeddings for a very large set of tests. And then what you do is that once you have learned this network, right, then you can keep this network frozen and just train the downstream task network. Okay. So let's say that you take all the documents on the internet, you spend a few $1 million to train the LSTM that does the next token prediction, and then you keep stealing the value of the embedding, the value of the hidden layers, to train a much smaller network that does sentiment score. Okay, so this is the real power of this, right? That you can sort of capitalize the complexity and cost of training a large network that does next token prediction, and you can use a vast amount of data to train this, and you can have a very large network. But once the network is trained, then you just look at the embedding and just learn from the embeddings. Okay. Good. So sometimes people talk about BLSTM, bidirectional neural networks, and this gives you a little bit of a headache. So just look at the figure and try to understand that basically you can imagine that you have a forward pass and a backward pass, right? So you see here that you're predicting the next token using the current token, and the other network is predicting the token in the past, given the token in the future. And of course, everything works fine, right? So it's the same sequential network. You fix a window. You want to either predict the next token or the previous token outside of the window. So everything goes too well. And the idea is that you can do the left to right on the right to left context to predict the data. And this is a quite straightforward extension, right? So here you see that we go left to right. Here we go right to left. And then how do you put these two objects together? The idea is that you want the network to learn from the context left to right and right to left. So what you do is that you take these hidden layers, right? So these are the hidden layers left to right. These are the hidden layer right to left. And what you do is that you stack them all together into a single state, and then you do the next token, the next token prediction accordingly, right? So remember that gives you a little bit of a headache, but it's here, right? So you're predicting either this token or this token. Good. Yeah, so BSTM, of course, outperform LSTMs because it's a more complex structure, right? So since you have more hidden states, then you can do better, right? And you can learn from patterns in the past and patterns in the future. Of course, it's slower to train, and also you need full data access, right? So basically the data cannot be in a streaming fashion, right? Because if the data is in a streaming fashion, that it doesn't work. You need to have access to the data so that you can move left to right or right to left when you do the training. Good. So yeah, deep RNN things are as expected, right? So let's read this. LSTM's units can be arranged in layers, right? So that the output of a layer unit fits on the other one. This is called a deep RNN, and the depth determines how many RNN layers you have, right? So you can have some sort of hierarchical RNN, and so each layer feeds the LSTM for the next layer. So the first time step, you feed to the first LSTM, which then produces an output, and the output is fed to the next LSTM. So when you go in Python, you can decide the number of LSTM and RNN that you have. And this is what you imagine, right? So this is the original sequence of data. This gets, this produces another sequence, and then this is fed to another RNN. So this is how you represent it, okay? So this adds some power to the representation, right? Because you can imagine that the redundancy of this intermediate sequence is lower than the redundancy of the original text sequence. So the idea is that you want to enrich the embeddings for each word. So you can use stack the direction, and you can also have a two direction. And then what you can do is that if you want to create a very powerful embedding, you can have another network, right, that decides how to fuse the hidden layers values of the different values. So yeah, so this is another nice picture. So we have an LSTM left to right. So this is a forward language model. Then we have another network that does the backward language model from right to left. And then these are repeated over multiple layers. And then in order to obtain the embeddings, you just stack things. Very good. Yeah, let's just look at the nice picture size. So this is the forward, this is the backward, this is layer one, this is layer two, and then you produce an embedding as a sum of the two, or as a, let's say, a nonlinear operation of the two. And you can do this. And what you obtain in this case is this Elmo, right? Oh, because, yeah, so you guys know that Sesame Street, I don't know, did you have Sesame Street? Probably you saw Sesame Street also on Taiwanese television. Yeah, it's a puppet show, right? So the joke is that this is called Elmo, right? Embedding of, let's stick to, yeah, anyway. So this is the way in which you produce, let's say, some very good embeddings, right? And the idea is that given enough training data, having tons of explicit connection between the vectors, it's very useful. Okay, so this is, remember, this architecture here is the Elmo embedding. Okay, good. So this is obtained through sequential modeling, and the network was always emitting one output per input. Okay, so that's you have a token in input and you have a token in output, and sometimes the sequence, right, has a smaller granularity, and we care about that. Let's see. So let's see sequence to sequence plus attention. Okay, so let's see the sequence to sequence modeling. So let's say that your input is a sentence of language A, and you wish to translate this into language B. So this is the English to German dataset that it's in challenge 5. Okay, so it's really suboptimal to translate word by word. So if you guys don't remember, maybe you remember, but the earliest day of Google Translate, right? The translation were based on some sort of statistical model, and so you will always have this issue, right? That the Google Translate will try to translate one English word in one Chinese word, or one English word in one German word, and of course, that's not how language works. So what we want to have is that we have a sequence in input and we have another sequence in output, and the two sequences do not have the same length, and there is not a one-to-one correspondence between one token of one sequence and one token of the other. So let's say in general we want to have n input sequence and m output sequence, and this is obtained using two RNN, one paired to the other, and there is an encoder RNN and a decoder RNN. And let's see how it works. So this is the famous example, right? The brown dog run over the fence. It's a twist, a tongue twister in English. So the idea is that we have the sequence in English, right? And then remember that here we have an encoder RNN, right? The encoder RNN starts the sentence and with a special token and ends the sentence with a special token. Okay, so what happens here is that we have the RNN, and the RNN produces this encoder, and then from this hidden state, we boot up the decoder RNN, and the decoder RNN will take this embedding and it will produce the sentence in French. So this will be a decoder RNN. Okay, so you see that the length of the sequence does not correspond to the sequence. This sequence starts with a start symbol and ends with the EOS special symbol. This is a different sequence. It starts again with the start symbol and ends with the EOS symbol. Okay. So then in order to train the network, in order to do the language translation, what you do is that you do backpropagation from the unfolded network, right? Where you have all the English correct sentence here, all the French correct translation here, and you have the token predictions, right? The token predictions that are here. And so you know that you're applying BCE, so that this token must be equal to this token, and then you just train the network, okay? So notice that the decoder RNN has to produce an EOS symbol. So in a sense, the network decodes when the network decides when the decoding is done. Good. And so this is called a sequence to sequence. So let's see if there is what are the issues with the sequence to sequence. So the idea is that the entire meaning of the sentence will have to be packed into this final hidden state, because then this hidden state is going to go into the next network, and this network is going to, the decoder RNN is going to become like a generator, right? So in a sense, you hope that the whole meaning, right, gets translated into this final embedding, and then this is a good bootstrap for producing a sentence, which is the corresponding sentence in French. And this is tricky, right? Because, if the sentence is very long, then we expect the scaling of the dimension of this hidden state to be very punishing, right? So instead, we could try to do something like that, which is our friend attention. Okay, so let's see what I would think about. The idea is that maybe, right, what you should feed to the decoder network will be a sort of a linear combination of some sort of summary, or maybe linear combination or subset of the hidden state of the encoder RNN, plus of course the final state of the RNN. Okay. This will work, right, in general, because then we can repeat this operation for all the different words that are generated. So we can produce this C, right, this sort of side information, right, from token to token for the decoder RNN, and this should do the trick. Okay. Of course, it's clear that we cannot feed all of the hidden states, because all of the hidden states will just create, first of all, a lot of confusion, because clearly not all the words here, they have a complex relationship, right? For example, le is just the article the. So it's clear that when you want to produce le as a token in output, you don't need to know that the verb, right? Because the article and the verb, they're distinguished, right? So if you feed all the hidden states, it's just going to create a lot of confusion. And of course, there is an issue of complexity, right? Because this hidden states, intermediate state, can be very large, so you don't want to, you don't want to, you don't want to create a network that is that complex. So the idea is we will want to have a mechanism which we will call attention mechanism that says this. This is a different sentence, but you understand. So for example, le is the article, right? The French article de will only depend on the, but will also depend on the word agreement. So this is the agreement on the European Economic Area, okay? And in French is l'accord sur la zone économique européenne. So the idea is that in French, the articles depend on the gender of the name. So agreement in French, right, has a gender, and the gender is male. So the article has to be chosen according to the gender. So ideally, what you want to do is that you want to have a network that sees it knows there has to be translated to the same article in French, but it doesn't know the gender. So you have to tell what is the subject of the article. Right. The other thing to notice is the verb. Here is signed, right? And in French is signé. Okay. But when we do this, right, we have to look at the temporal aspect, right? So here is was signed. So this is in the past. So the verb signer, it's already conjugated to the past tense. Okay. So the idea is that you want to have this mechanism that sort of correlates the words according to in the two sequences and provides the information needed to produce the next token in the code. Okay, so this is called attention, and this is what we're going to do next. Now we can go back to attention, and the attention is here. Let's see if we can replace where we started, right? Sequence to sequence decoding. I see what happened to that. I see what happens. Yeah. Good. Transformers. So, okay, good. Sorry, guys, just checking. Oh, this is attention. Finally. Yeah, good. Okay, so now we can work on this. Transformers, very good. So we discussed all of this. We discussed the type-based and the token-based. We discussed the sequence attention, right? So this is the mechanism here. And now, this is how the attention mechanism works. And now we can discuss transformers, okay? So we understood how each word in a sequence is transformed into a representation, which is based on the context. And then we want to determine, right, inspired by this idea of attention, we want to determine the influence of the embedding of a certain word to the translation. Okay? So let's just think of it in this abstract way, right? So this is the input sequence in English. This should be the translation in French. And we want to decide, right, with which weight which weights to choose in order to provide a side information to the decoder, which is small in size and it's salient in producing the prediction. Okay, so we decided we like linear combination because linear combinations are simple to implement and they have some smoothness properties. So we decide that we want to predict these weights A, and then what this guy gets, and the token 1 will be A multiplied by the embedding of the different word. Okay, good. So this is the task for the day. Let's see how we can do it. So the idea that X1 is the input token. And we want to have a query. We want to define for this sort of set of input of xi the following: a query qi, a key ki, and a value vi. Okay. And now we're going to put them together. The idea is that for each token xi, we have the q1, k1, v1. For token 2, we have q2, k2, v2. Very good. And the idea is that we have 3 weight matrices, right? So we can stack all of these vectors into a matrix. so that then I can describe the Qi as the big matrix WQ times Xi, Ki the big matrix W times Xi, and so on and so on and so forth. And these are input tokens, so they are vectors. These are matrices, and if my linear algebra is correct, then a matrix times a vector, it's equal to a vector. Okay, so the mathematical operation is this one here. So the idea is that we have the score, a certain score Si, which represents how much attention should the decoder pay to the token I, which represents the word Vi. Okay, so Si is a score. So the idea is that we want to learn how to score the token, and the score is going to obtain as the product of the query times the key, right? So remember, the query is Qi, and the key is K1, okay? And then we repeat this V2, so the query Q1 times Q2 will give us the score for the second word, third word, and fourth word, okay? So these are just some numbers, right? Good. Then the alphas, so remember that the alphas are the coefficients here. The alphas are coefficients here. These alphas, they have to be scaled between 0 and 1 clearly, right? So these alphas are represented as sigmoid, right? Sigma applied to the score divided by 8. Don't ask me by why 8. Why 8? Some reason. Anyway, so it's a sigma. Of course you have to. It has to be a probability distribution. Right? So something. The normalization means that the score must be divided by 8. Okay, so these are then the value A's, and then we multiply the word embedding by this value A's, and then we provide it as a side information. Good. So now the Z is the linear combination of the word embedding multiplied by the score, and it's just a linear combination of scalars times vectors, right? So these are weights times vector. This is the hidden vector. So the Z is the linear combination of weights times the hidden vector. Okay. Good. For Z2, I repeat, and for Z3, I repeat, and for Z4, I repeat. Okay, good. So the idea is that we want to learn these big matrices, and then we want to apply these matrices to Riemann field. Okay? Good. So this is another example. Oh, now it's done. I can divide by 8. You put the Z's, and then this will produce what is called an attention head, right? So you can teach to a network to produce these matrices, so that for given this sentence, this is the linear combination of the embedding of the word that will be fed to the decoder network in order to produce the French translation. This is again this challenge 5. It's a great mechanism, has been used for many things. And self-attention may seem so. Self-attention is self-attention is when the encoder and the decoder are the same. So you're using the self-attention for prediction, but of course you can also use it for translation. Okay. So remember, this is the encoder RNN. This is the decoder RNN. So we multiply the encoder hidden layer with the attention A1 in order to create the content vector C1D. Let's see how this goes. And so the C1D is the linear combination of the hidden vector there. And then, and then this is the mechanism that you use for self-attention. Okay, so you apply the attention mechanism to the context of the vector itself. Good. So there's usually just a change of words. So remember, this is a query key values. In self-attention, there is a certain the decoder. This is the decoder hidden states, and this is the encoder, and this is the encoder. Good. Okay, so the people generally like attention because it provides a very succinct representation of relevance of the word embeddings. And let's see what happens here. So what you can do is that you can also put it in a FFN layer, in a fully connected layer, And then, yeah, and then you can train everything in parallel like an LSTM. So now this is the following, right? So here we have the input sequence. Then we have the self-attention head that sort of summarizes the content of the hidden layers. Then we have the residual connection, and we have another sequential network, and then what we have the representation of the process, right? So this is what is called the transformer encoder. Okay? So transformer encoder architecture, and of course our French GPT has many transformer encoder inside. And so the idea is that when you do this, you have lost, you've done multiple layers, multiple sequential layers, right? So the positionality of the word has been lost because this attention mechanism is able to, change, in a sense, reorder the sequences, right? So if the attention waits a hidden layer in at the bottom of the attention head, you can effectively reorder your sequences, right? And so this loses the positionality of the word. And so sometimes what you do is that you also attach a positional encoding to the token, right? And the positional encoding is sin I cos I. So this is, you understand trigonometry, but basically it's you give sort of an index. This corresponds to, let's say, some sort of smooth index of what was the original position of the word, and this improves the performance generally. Okay. Now that we've done single attention heads, then we can have multiple attention heads, as you will do with deep neural with a convolutional neural network. So you can have multiple encoder decoders. You can stack up your encoder decoders architectures, and so initially this was done for machine translation. So that's how they stack the encoder and decoders, right? So you have the multiple attention heads. Each of the attention heads feeds one of the attention heads of the decoder. Very nice architecture. And then you have both attention heads and self-attention heads. So that things can get infinitely complicated in machine translation, as you can imagine. And the issue with attention heads is that the complexity is very large. Since you are doing these multiplications, right? So you have these large matrices that produce the attention through these linear combinations. So it's very inefficient in the sense that you have many parameters, right? So people love attention head. I guess people love attention heads, but they have been trying to move beyond attention for the past these many years. Yeah, so this is just the machine translation performance, and now you can go through this and you can see how machine translation has improved. Okay, very good, guys. So Bert will do it next time, right? Also because it's the context of the challenge, so you can, I think you can do it yourself, and by the time you get there, you guys should have already done your challenge. Let me say goodbye to you guys here. Remember, please, to okay, I'll say goodbye here. I'll stop the recording, right? So the people in the future, bye-bye. So just for everybody, just remember that